Today we're going to talk about doing the antiderivative using substitution. Substitution is our first sort of big trick for doing the antiderivative. It's a weird trick, but it's actually very powerful. It's kind of tricky trick to do, but let's see if we can do it. The substitution, it is based on doing the chain rule. So the chain rule, I will refresh your memory. It says the derivative of f of g of x is f prime of g of x times g prime of x, right? That's the chain rule. Now, this is the chain rule written as a derivative, but I can write this instead as an antiderivative. The derivative of this is that. That means the antiderivative of this is that. So it would say this: integral f prime g of x, g prime of x dx equals f of g of x. So this is actually the formula for the substitution, although I do not recommend you memorize this like a formula because this is a little too complicated to think about as written. You should think of this more like a process. There's a procedure that we do to do the substitution, but the idea here is when you have f prime of something with a function stuck on the inside of another thing, followed immediately by the derivative of that same function, then the antiderivative is just the antiderivative of what you saw in here, or the function that this is the derivative of. There's a cute way that we can write this, which makes this all a lot clearer. So I'm going to let u equal g of x and du equal this thing right here, g prime of x dx. And then what the rule says is integral f prime of u du equals f of u. All right. The idea is you begin with something which looks pretty complicated. If you have a complicated function which involves something stuck inside of something else followed by some other stuff, if you play your cards right, you can convert this into something that looks much simpler. Just f prime of something followed by d something. It's called the substitution because you begin with some complicated thing in terms of the variable x, and you end up replacing it with a much simpler thing in terms of a different variable u. And then the answer here is given very simply in terms of u again. Really, we just need to do a few examples. All right, the integral of 2x times x squared plus 10 to the power 6 dx. First off, can I just say, when you look at this, you should immediately identify that this is too complicated to do by the methods that we talked about last time and the time before. Really, all we know how to do so far is just a polynomial or something involving exponential functions. This is neither of those. We have x squared plus 10 inside of this 10th power. When you have a weird thing inside of another weird thing, you definitely need to use some kind of trick, and that trick is usually the substitution. So what we're going to do is, I said before, the substitution involves changing from variables using x into variables using u. And what makes it difficult is it is your job to decide what the new variable u should be in terms of x. And you have to make this choice. So I'm going to tell you how to choose it in this particular example. We will discuss in more detail exactly how you should choose the u. But in this example, just because I know what I'm doing, I'm going to choose u to be x squared plus 10. I might as well tell you right now, you look for something which is stuck inside of something else, and you choose the inside to be the u. This is because of the u substitution's sort of roots in the chain rule, in which you have a function on the outside and a function on the inside. You want the u to represent the function on the inside. So I choose the u to be the thing inside the parentheses here. And now we try to rewrite everything. Before that. So I choose the u to be the thing inside the parentheses here. And then you find the du. Du is always the derivative of u. Remember where this came from a moment ago? I said we're going to let u be g of x and du be g prime of x dx. So du is always the derivative of u. In this example, that would be 2x followed by dx. Du in this case, is 2x times dx. Okay, and now you look at the original integral here, and I'm going to try to rewrite all of that stuff using only u's, not using x anymore. So this becomes, first of all, I'm going to replace the u just where it is. It's going to say 2x, and then here I have u to the power 6, right? dx. All right, I've replaced some of the x's by u. My goal is to replace all of the x's by u's and du's. Okay, what can we do with this? I have u to the 6. I like the way that looks, but I now have these leftover things, the 2x and also dx. It is helpful in my experience to try and gather them together. So I like to write all the stuff involving u's first because I'm settled with that, and push all the leftover stuff together at the end. There's that. Now, do you see how can I substitute 2x dx using u's or du's? Well, I got lucky. This actually equals du. So this is equal to integral u to the 6 du. And now I have completed the substitution. Everything has been rewritten, and now I'm using only u's, no x's anymore. What's the point of this? This now is a very easy thing which we know how to find the antiderivative of. It is just a power of u. You should think of this like a power of x, only the variable is called u instead of x. It's just a power of u, which means I increase the power by 1, so it becomes u to the 7, and then I divide out by the new exponent, and of course I write the plus c. And this is basically the answer. I have done the antiderivative. The only thing remaining to do is, the original question was in terms of x, right? A function with the variable x. You should write the answer also with the variable x. And the way to do this is just by replacing the u. Do you remember what the u was? I erased it, but the u was, wasn't it x squared plus 10, I believe? All right. So the final step is just to write your answer in terms of x. 1/7 x squared plus 10 to the power 7 plus c. This is my answer. All right. Let me just write down the basic steps here. So first of all, you choose the u, and let me just say pick the inside. Now you have to get a feel for exactly what this means. In that example, it was pretty clear there was something inside of parentheses, so that's a good choice. Sometimes you need to choose something which is inside of an exponent, inside of a square root sign. Sometimes you choose something which is like inside a denominator. This is the tricky part. There's no hard and fast rule about how you're going to choose the u. You have to choose something that works, and it comes from seeing a lot of examples, practicing. Okay, anyway, first you choose the u, then you find the du. How you find the du is it's the derivative of u followed by dx, right? And then you try to replace or substitute all x's with appropriate u's, right? In the example we just did, I saw x squared plus 10 in the formula, so I replaced that by u. And then the other stuff, 2x dx, I replaced by du. All right, substitute all the x's with appropriate u's. And then finally, do the antiderivative. That was this step here. U to the 6 became 1/7 u to the 7. It is in this step in which I stopped writing the integral sign in the du because I just did the integral in that step. And then very last step, which is always easy, put the x's back in for u's. Replace the x's. All right. This is not easy to do. I want to do 4 more examples. Can you believe it? Do we got time for that? We'll see. Example number 1, integral of 3x squared times the square root x cubed plus 1. We begin by choosing the u. Remember my advice, choose the u to be the inside of something. Do you see any something that has an inside? I think I do. How about the inside of this square root sign? So I'm going to choose u to be x cubed plus 1. That means, next step, find the du. The du is always just the derivative of u followed by dx. So in this case it is 3x squared dx. All right, and now I go back here and I try to plug these things in where they go. So first of all, I will just plug the u where it goes. It now says square root of u, and I left everything else like it is. And like I said last time, I like to sort of gather all the u stuff at the front and then push all the x's towards the end, just to let me have a feel for what I'm working with here. I have 3x squared and a dx. All right. What can you do with 3x squared dx? That equals the du. Isn't that nice? There's a sense in which I kind of got lucky here. If that wasn't just so that it matched, then I would be screwed at that point. You do have to get lucky to some extent in order for the substitution to work. Okay, anyway, this is du. So this is just square root of u. Would you mind if I wrote u to the 1/2? As always, it's not very helpful to write the root sign in this class, at least. U to the 1/2 du. All right, I have completed the substitution. It's all u's now. I'm going to do the antiderivative. You increase the power by 1, you get u to the 3/2. You divide by the new power. 1 over 3/2, or would you mind if I wrote 2/3? It's a reciprocal of 3/2, all right? And then a plus c. Almost done. That was the antiderivative. Final step, plug the x's back in. So instead of u, I'm going to put x cubed plus 1. So my final answer is 2/3 x cubed plus 1 to the 3/2 plus c. That's my answer. I hope that's what you got. Example number 2. This one is very similar, although you will see this requires one extra step. The ones we've done so far have actually been easy because you didn't have to do this one step that you do usually have to do one extra step. And I will tell you what that step is. This won't make sense right now, but you'll see what I mean in a moment. It says divide by a constant to make the du match. Let's see you'll see what I mean when we get there. I forgot my dx. Okay, we begin by choosing the u, as usual. You choose the u to be the inside of something. I'm going to choose the inside of these parentheses. So u shall be what? X squared minus 1. That means the du, taking the derivative, is 2x dx. Du always consists of the derivative followed by dx. Okay, let's try and plug them in. I'm going to begin by just plugging the u where it goes. This is x here, and then this becomes u to the 2/7 dx. Okay, let's gather the u's to the front and then write all the leftover x's at the end, just because that helps me to be clear on what I'm doing here. U to the 2/7 times x dx. And now is the point when you look here and you try to match this with the du, but they do not match because this is x dx, whereas this is 2x dx. They almost match, but not quite. What am I to do? What's a fella to do in this situation when they don't quite match? I told you what to do. Divide by a constant to make the du match. What I mean by that is right here, du equals 2x dx. I'm going to divide this 2 to the other side here. 1/2 du equals x dx. How you like that? Now I can put that right there. So this x dx, it's not du, it's 1/2 du. So this is integral u to the 2/7 times 1/2 du. And now we can proceed as usual. Before doing anything else, I'm going to take this as a constant multiple. It can be pulled all the way out of the integral. Remember that rule? We're going to be using that rule a lot in this section, actually. A constant multiple can be pulled all the way out of the integral. So all we're left with is integral u to the 2/7. I'm going to leave the 1/2 out front. All right, what is the antiderivative of u to the 2/7? I increase the power by 1. 2/7 plus 1. I think that's u to the 9/7. Divide out front by the new power. Dividing by 9/7 is the same as multiplying by 7/9. 7 of 9, if you will. Plus c. All right. I just did the antiderivative. This is almost my final answer. The final answer is when you replace the u by x's again. So combining these fractions, if you like, 7/18 times x squared minus 1 to the power 9/7 plus c. That's it. divide by a constant. Usually you do need to do this step because it requires a bit of magic for this to just coincidentally match exactly. Usually it doesn't match exactly. You have to adjust yourself by dividing a constant. Example number 3, x over x squared plus 1. This one is especially weird because when you look at this, there doesn't seem to be any inside of anything, all right? Because there isn't any parentheses with a thing inside of it or a square root with a thing inside of it or anything like that. If that happens, then really your only options are just to try and choose something and see if it works when you do the substitution. See if you can actually complete the substitution. My choices that occur to me would be either x or x squared plus 1. It turns out actually choosing u equal x is never a good idea. It's not really wrong per se, but it never makes the integral any easier to do. The whole point of the substitution is to transform the integral so it becomes easier to do. U equals x will never do it. Let's try u equal x squared plus 1. All right, then the du would be 2x dx. I left out the dx again. I'm losing it. All right. Okay, let's see. I'm going to replace x squared plus 1 with u. So I have integral x over u dx. Okay, and as usual, I'm going to try and write the u stuff first, followed by the leftover x stuff. Now, when you do that, I'm going to pull out this division by u. I'm going to write as 1 over u because I like to write this as the u part times whatever x stuff is left over. What x stuff is left over? The x and the dx. So it's like that. All right. I broke up that fraction because I like to see the x and the dx part all together. And now what do I do with x times dx? Well, I see it right there. We can divide the 2 over, and I get x dx is 1/2 du. Actually, it's just like the previous example. All right, so this becomes integral 1 over u times 1/2 du. And I can do the integral now. Let's take the constant out front. This is what we always do. And now the antiderivative of 1 over u. Do you remember? The antiderivative of 1 over u, antiderivative of 1 over x, it is the natural log. So this is 1/2 natural log, absolute value u, plus c. And then finally, the last step, which is always easy, you plug the x's back in. 1/2 natural log, absolute value of x squared plus 1, plus c. That's it. Example number 4. Integral of x squared e to the minus 2x cubed plus 4 dx. This is a crazy one. I'm going to choose the u to be the inside of something. In this case, you should choose the inside of the exponent. So I'm going to say u is all that stuff up there. Minus 2x cubed plus 4, right? Du will be the derivative of that. I guess minus 6x squared dx. All right? Okay, let's see if we can plug everything in. First, I stick the u where it goes. E to the u, right? dx. Now I'm going to gather the u stuff in front, e to the u, and what remains I'll put over here, x squared dx. All right, what can I do with x squared dx? You look here and you try to match that with the du. It does match apart from this constant here, so I'm going to divide that constant. Negative 1/6 du equals x squared dx. Great, so this x squared dx turns into negative 1/6 du. We continue as before. Pull the constant out. E to the u du. Now we do the antiderivative. Anyone remember what is the antiderivative of e to the u? Integral of e to the x. The integral of e to the x is e to the x. So the antiderivative of e to the u is e to the u plus c. All right. I hope this doesn't bother you. You might say, like, what? You didn't do anything in that step. Well, I did. I took the antiderivative. It's just a fact that the antiderivative of e to the u is e to the u again. So it looks like I didn't do anything. I did do something. I took the antiderivative. Okay, this is almost it. The final answer, I replaced the u's with the x's. So I go minus 1/6 e to the power negative 2x cubed plus 4. plus c. All right, that's it. I got one more, just one more. Can you handle one more? These are tricky, which is why I wanted to do so many. Oh, you're gonna love this one. I can tell you already do love this one. Natural log of x divided by x dx. This is yet another one where there doesn't seem to be anything inside of anything here. And I told you last time that choosing u equal x is never going to work. So my only other option really is choosing u equals ln of x. There really isn't any other promising choices that I could make here. All right, u is the natural log. Okay, then what is du? It's the derivative of u. The derivative of ln x is 1 over x. I hope you remember that. Followed by dx. We always include dx as part of the du. Let's see if we can do it. So this thing here is going to equal, all right, I'll put the u up there like I do. And now to separate out the u's from the x's, actually it looks like one I did 2 times ago, right? I want to write it as if these things are being multiplied on the inside rather than, I don't like fractions like that. So pull apart the u stuff first, the x stuff afterwards, and then I look here and I try to match this with the du, and actually we get lucky, it matches exactly the du. So this becomes integral u du. Whoa, okay. Can we do the antiderivative there? Yeah, I think so. The antiderivative of u, this is like u to the 1. I increase the power by 1. I get u squared. I divide out by the new exponent in front. Put my plus c. And that's pretty much it. 1/2 u squared plus c. Final step is to put the x's back in. 1/2 ln x squared plus c. And that's the answer.